All right, next we're going to go from a set of parametric equations to describe a curve in the xy plane and convert it into an equation which is one variable. So we need to eliminate the parameter. So here, you take one of these, it doesn't matter which one. Generally, it'll be the one, in this case, where you can easily solve it. In this case, it's a linear case. So I wouldn't necessarily want to solve for t in the first parameterized equation because I'd have to take square roots and I have a plus or minus. Okay, so here it's easier just to do this one here. Okay, so here solving for t, you get t equals y minus 1 over 2. Then you're going to substitute y minus 1 over 2 into the x equation for t. So instead of t squared, you'll have y minus 1 over 2 quantity squared. And now you have x, when you do the simplification, equals y squared minus 2y minus 11 over 4. So here I've got an equation that relates x in terms of y. So I've got a relation there, and it's going to be a parabola that opens to the right because of the positive coefficient on y squared. So here I've got a relation. It's not a function, but that's okay. Oftentimes when you do have a set of parameterized equations, it's because the graph itself is not a function. So this is one of those classic cases. We take one of the equations, solve for t, substitute back into the other one, and we get a relationship, in this case relating x in terms of y. All right, so there's our first example of converting a set of parametric equations into an equation where we've eliminated the parameter t. All right, so here we've got two more examples of eliminating a parameter. And here the first set of equations have got x of t equals root 2t plus 4. And the second one is y of t equals 2t plus 1. So in the first example, we took the linear case because it was an easy equation to solve for t. Let's go ahead and be a little bit more daring and try to solve for t in the first parametric equation here. So to do that, you would square both sides. You get x squared equals 2t plus 4. Subtracting 4 and dividing by 2, you'd get x squared minus 4 over 2 would be equal to t. Then you would plug that into here. So you have twice the quantity x squared minus 4 over 2, but the 2's would divide. So here I would just get x squared minus 4 plus 1, give me x squared minus 3. Let's go ahead and look at the details there. I verbalized it. Okay, so here's x equals root 2t plus 4. Squaring both sides, I get 2t plus 4 equals x squared. Take away 4 divided by 2. T equals x squared minus 4 over 2. Replacing that, or substituting it into the parameterized equation for y. So that's to be 2 times t, but t had a factor of 1/2, so those 2's will divide. Give me x squared minus 4 plus 1 will be x squared minus 3. All right. Now remember, this was parameterized from minus 2 to 6. Let's make sure that the process of doing that, I don't have a domain restriction there because 2 times minus 2 is minus 4, plus 4 is 0, so that's still well defined. Okay. So here they check that to make sure there wasn't any type of concerns with that domain restriction. All right. Again, our final result, y equals x squared minus 3. It would be a parabola, but do be careful because we only have from t equals minus 2. That means x equals 0 to, what was the other last part of it? T to 6. And so when t equals 6, oh, here it is, right here. 2 times 6 is 12 plus 4 is 16. Root 16 is 4. So this is going from 0 to 4 in our graph. So x of 0, x of 4. Okay. So here we're only getting part of the parabola because our parameterization was from minus 2 for t value and to 6 for a t value, which corresponds to an x value of 0 to an x value of 4. All right, let's look at the next one. Minimize this. So here I've got x of t equals 4 cosine t, y of t equals 3 sine t. And notice in the previous example I had 4 cosine t and y was 4 sine t, and we got a circle. So here they're not the same coefficient, so this is going to be an ellipse. Okay. So how do I solve for t? You don't really want to do an arc cosine or arc sine to do this. Okay. So you want to use the fact that sine squared t plus cosine squared t equals 1. All right. And what I would do is rewrite this as cosine t, all right, equals x over 4. Sine t equals y over 3. And then use Pythagorean's theorem that cosine squared t plus sine squared t equals 1. So that means x over 4 quantity squared plus y over 3 quantity squared would equal 1. Let's look at the details. Okay. So here's x equals 4 cosine t, y equals 3 sine t, and they immediately divide by the coefficient on both these trig functions. All right, so cosine t is x over 4. Right? Sine t is y over 3. And then use Pythagorean's theorem. Right? Cosine squared t plus sine squared t equals 1. So that means x over 4 squared plus y over 3 squared equals 1. Carrying it out, I've got x squared over 16 plus y squared over 9 equals 1. And there's my relation. Right? This is not a function. This will graph out an ellipse, right, where the major axis is length 4 and the minor axis out 3 units. All right. Here's the major axis goes out 4 units, and the minor axis goes out 3 units. All right, notice that the parameterization t was between 0 to 2 pi, so it does in fact draw the complete ellipse. Now, if it didn't go all the way out to 2 pi, it would only be part of that ellipse. Okay, so we've got 3 nice examples of going from parameterized equations to equation with just x's and y's. There's our ellipse. Here we had a parabola, and in the first one that the textbook did, we also got a parabola that opened up to the right.